This video is about analysis of polynomial functions. So I'm starting out with a really complicated looking function just to prove to you that you can actually tackle an analysis of this function based on what you already know without graphing it on a calculator and without foiling all of these different pieces together and turning this into some huge complicated function. Because the way I look at it now, it's already been broken down for us. It's been what we call factored, and it's written in a factored form. So we can see each of the factors that leads to this polynomial function the way that it's written now. The first question you're going to be asked is to identify what is the degree of this polynomial. Now, the degree, as we know, is the exponent, the highest exponent there, so the exponent of the first term when it's in standard form. Now, this is far from standard form. We would have to write all of these factors out and distribute for like hours in order to turn this thing into standard form. But of course, that's not what I'm asking you to do. What I want you to do is imagine that you do that. Imagine that you write all of these factors out. So this x minus 3 has a squared on it. It's there twice. This x minus 1 has a third power on it. It's there, this x plus 1, it's there 3 times. And this last factor has an x squared in it, right? So it's sort of like that x already has a degree too. What would happen if I FOILed all of this out? Is that the first term in my final answer is simply going to end up being the first term of each of these factors multiplied together. That's just what ends up happening when you FOIL this whole thing out. And the first terms, I can multiply those without too much rigor. So if I just take a 2x and multiply it by an x, an x, an x, an x, an x, and an x squared, I can see that my first term is going to end up being 2x to the 1, 2, 3, 4, 5, 6, 7, 8th power. I just counted all of the degrees that I had, added them all up together, right? So I ended up with 2x to the 8th power as my first term. And of course, it would have many other terms with complicated coefficients that come after that, but I don't need any of those to answer what is the degree of this polynomial. So basically, we're just counting up in the original function how many x's we see. And of course, anything that's squared, that x counts twice. Anything that's cubed, that x counts 3 times, and so on. So there end up being 8 x's in this function. It's going to be an x to the 8th power for the degree. How many zeros will it have? Zeros, as you know, are the x-intercepts. And we learned that the number of zeros is equal to the degree. Now, some of them may be imaginary and some of them may be real, but we're not asked in that great detail. So we just have to say that there will be 8 zeros. Because the degree was 8, there are going to be 8 solutions. The next question actually wants us to find them. Actually find the zeros of this function. When you find the zeros of a function, you basically set the function equal to 0, right? You change the y value to 0, and then you see if you can solve for x. If it had been FOILed out in standard form, that would be really complicated to do without a calculator. But because it's already factored for us, we can take each one of these factors, like the 2x, and set it equal to 0. We can take the x minus 3 squared and set it equal to 0. And we can take the x plus 1 cubed and set it equal to 0. And we can take the x squared plus 9 and set it equal to 0. Because what we know is that when we multiply many factors together and it equals 0, that each factor, at least one of the factors has to equal 0. So you can easily solve each of these without much work, right? Here, x is going to equal 0. Here, x is going to equal 3. Here, x is going to equal -1. And here, we do have to do a little bit of algebra. Subtract the 9, move it to the other side. This is where you do the square root of a negative. And the square root of -9 is plus or minus 3i, right? Anytime you do a square root, there's a plus or minus in front. If I was to add up or count up how many solutions I just got, I only got 1, 2, 3, and then the plus or minus counts as 2 different answers. So 1, 2, 3, 4, 5 solutions. And that's why it says here, use the words multiplicity of for any repeated zeros. And if you remember from when we talked about functions crossing the x-axis, right? If it bounces the x-axis and turns around, right? It doesn't cross it, but it bounces it there. That's because you've had something like this repeated 0. This x minus 3 with a squared on it counts twice. So the solution x equals 3 counts twice. So underneath it, we write that this solution has a multiplicity of 2. That's just a fancy math way of saying this one counts twice. The one that had a third power on it counts 3 times. Oops, I gotta spell it right. So we say that this one has a multiplicity of 3. So rather than writing that it counts 3 times, we use the words multiplicity of to show how many times that answer counts. And now when I count them up, x equals 0 is one solution. X equals 3 counts twice, so 1, 2, 3. Then I have 4, 5, 6 because my negative 1 counts 3 times. And then I have 7, 8 answers because my plus or minus 3i is 2 different. So I got the 8 answers that I was looking for. Some real, some imaginary, some repeated. Will the leading coefficient be positive or negative? Well, we already imagined foiling out this whole expression. And the first term ended up being 2x to the 8. So that means that our leading coefficient is just a positive. In this case, it's positive 2, but wasn't even asking about that. So positive. And that means we can determine the end behavior. So if my first term is a positive, and it's an x to the 8th power, which is an even number, that means the graph is going to look something like this. Now it's going to turn around in the middle, and it's going to cross the x-axis, and it's not the middle behavior that I'm asked, it's the end behavior. So when we're describing this end behavior, we just have to imagine what's happening on the left, which is that as x goes to negative infinity, f of x approaches infinity, positive, because it's rising up. On the right, which is when x approaches infinity, f of x also approaches infinity. All right, so we've described the end behavior. So we just did a whole analysis of this function, this long, complicated degree 8 function, and we were able to even find the x-intercept, or the zeros, without having to look at it on a calculator or expand the whole thing using FOIL. So as you probably figured out, the zeros are the x-intercept when you look at it on the graph. So you're basically, when you find the zeros, you're basically able to start graphing this function. We haven't actually put any of these on the graph yet, so this is sort of our first foray into putting one of these functions onto the coordinate plane. When the function's already factored for you, like the one is here, this f of x, you can see that the zeros are going to be located at 0 equals each one of these factors. And if you don't show all this work, that's absolutely fine. You can see what they are sort of just by looking at it. So those 3 locations, those 3 real zeros, are points on the x-axis of this function. I know from, if I were to FOIL this all together, from looking at just the first term of each factor, that this is going to be a 1x to the 3rd as my first term, which means that the end behavior is supposed to start down, wiggle around, and end going upwards. That's what a positive odd function should look like. So now that I have these 3 points on the coordinate plane, and I know I'm supposed to start low and end high, I can actually sketch this graph without using a calculator. The only thing that I'm sort of making up is how high and how low to go, right? I knew I needed to go through those 3 points. What I didn't know was how high I was supposed to go in between here and here, and how low. So basically, I made up the turning points. I would need a calculator in order to get those to be more exact, or there's some more complicated work we could do to figure out how high those need to go. For now, I'm happy with just the sketch. Just make sure that your end behavior is correct and that your 3 x-intercepts are correct for this function. Of course, if any of my zeros had come out imaginary, if they had had an I with them, then there's no way to graph those on the coordinate plane, so I wouldn't have a point for those. And so there's no way for you to really graph an imaginary zero or know that it's there unless you use a graphing calculator to see the shape of the function. So we've talked about this before, but we've never actually written it down. Then an even multiplicity, so that means if you have a repeated zero, and if it's repeated an even number of times, like it counts twice or it counts 3 times, then the function is going to bounce but not cross the x-axis there. And then if it has an odd multiplicity, that means that it does actually cross the x-axis there. So what that means for a function like this, so if I set this equal to 0, and I try to solve each of these factors, I get the solutions x equals 0, x equals 3, and x equals negative 2. The x equals 3 has a multiplicity of 3. It's counting 3 times because it has a third power on that factor. And this negative 2 has a multiplicity of 2 because because it has a squared on that factor, that one counts twice. When I put these on the coordinate plane, I'm going to put a point at 0, a point at positive 3, and a point at negative 2 on the x-axis. And I know that this function is going to ultimately end up being a negative, first term is going to end up being a negative x to the 6th power, and then all the other terms I'm not that concerned about. How did I get negative x to the 6th? I multiplied a negative x rather, times this x 3 times this x twice. So it ends up being negative x to the 6th power. Negative x to the 6th power is supposed to look something like that, right? It has end behavior where it's down on the left, it's down on the right, and it turns around some number of times in the middle, but I'm not sure how many. When I want to sketch this function, now I need to pay attention to multiplicity. When I start down low and the first point I reach is that negative 2, the fact that it has an even multiplicity, meaning it counted an even number of times, counts twice, means that I'm going to bounce off of the x-axis and not cross the x-axis there. It's going to do one of those. Then I somehow need to get back up to 0, so I'm going to have a turning point, and again, I'm making up the turning point. I'm not trying to be that specific about how low or how high to go, but I do know I need to get back to 0. When I hit 0, I am allowed to cross it. That one does not have an even multiplicity, it just counts once, so I cross. And when I get to 3, it also has an odd multiplicity, right? A multiplicity of 3 means it's counting an odd number of times, so I get to cross it there and then start decreasing. So that's my general sketch for this function. All right, and then the second half of the homework is transitioning to sort of working backwards. So if I give you the zeros of a function, and I ask you to write me the polynomial that got those, it's actually pretty simple. It's asking us to write a polynomial function of least degree. That means don't throw in any more solutions that are not already given to you, though I could do that. And it would still have these 3 solutions. It would just have additional ones. So that's basically just don't do more work than I'm asking for here. Just use these 3 solutions and come up with the function that has these as the x-intercepts. Which means if positive 1 is one of the answers, the factor x minus 1 must have been in the function. And if positive 3 is the answer, then the factor x minus 3 must have been in the function. And if negative 4 is a factor, then x plus 4 must have been in the function. The other thing that it says in these instructions is well, it doesn't say it in the instructions, it should though, is that the leading coefficient that we want is just a 1. So I'm not asking you to put any numbers in front of x, though you could. Let's just leave all of them as simply 1x, so that we can get all of us the same function as the result. This is it, basically, but I do want you to practice expansion, so I am going to want you to expand this out and write this thing in standard form. So I'm going to not do that here in the interest of time, because I know you know how to FOIL and expand. But I am going to write the note. You should expand it and put it in standard form so that we're practicing getting our function written out in the right order, which gets a little bit trickier if I give you not a whole number, but rather an irrational number as one of the zeros. So let's talk a little bit about those. Complex and irrational conjugates is just a fancy way of saying imaginary numbers and irrational roots always travel in pairs. And I use the word travel in pairs. That's not like a math thing, that's just the way I remember it. They always travel in pairs because they always have a plus minus in front of them, right? So if I knew that positive square root of 2 was the solution, then I know that negative root 2 must also be one of the solutions, because there's no way to obtain that as the answer unless this was the step that came right before it. So if you have x squared equals 2, and then you do the square root of 2, of course you're going to get plus minus root 2 as the answer. So every time you do a square root, you end up with 2 answers. They're called conjugates, right? These are irrational conjugates. They're called conjugates because one is plus and one is minus. Similarly, when you do imaginary numbers, the only way to get them is to have something like, maybe I'll make this one a little bit more complicated. Okay, so if I was to solve an equation like this, When I square root, which is the only way to get inside of these parentheses, I end up getting plus or minus the square root of -4, which is 2i. And then, of course, I have to subtract this 1. So these actually are the solutions for x, and there are 2 of them. They're called conjugates because one has a plus in it and one has a minus. They're not opposites of each other. They're conjugates of each other. The reason why that's going to matter is because if I give you a question like, let's try this one. Let's try this one. If I give you a question like this, I'm asking you to write me the polynomial that has these solutions. Notice 2 plus root 5, this is one answer. There's not a comma in the middle of that. That's like one answer. And that means that 2 minus root 5 is also on this list. And I'm being tricky by not giving it to you. So that means you're going to have to remember to put it on the list as well. Because there's no way a function could have 2 plus root 5 on the list without having 2 minus root 5 on the list as well. So that means I actually have 4 factors for this. X minus 1. I have x minus 3. I have something that looks really complicated, but it's actually going to be okay. And then I have this one as well. Notice both of those I put as x minus because the 2 is positive for both of them. The 2 is not changing sign. It's the root 5 that has 1 plus 1 minus. So since the 2 in both is positive, when I fill it into parentheses, I'm doing x minus and another x minus. And when you FOIL this all out, it's just a little tedious, but it's not that complicated. These two you'll probably want to FOIL together first. And then this gets a little cumbersome, trying to multiply this all out, because you have 3 terms in each parentheses. But we've practiced multiplying trinomials with other trinomials. It's a lot of work, but it shouldn't be that complicated. I'm not going to finish that one out either, in the interest of time. And then the one thing I will remind you of for this last example, which I'm not going to do all the way out either, is that if you have to do an imaginary root, you still can say this and this, right? We want to treat them separately when we fill them into the parentheses. I did one as x minus 1 plus I root 2, and the other one is x minus 1 minus I root 2. Again, they look complicated, but when you FOIL them out, I will remind you that anytime you have I squared, you can replace it with a -1. So that's going to help make it kind of more simple towards the end. And you'll realize that eventually all of the i's are going to either cancel out or get replaced with an I squared, so that you will not have I in the final answer for your polynomial. So I'm just going to let you try it. We'll see where you come in with your best attempt on these, and then we'll do any troubleshooting that you need to do in class.